Why earthquakes aren't isolated events. Our planet's crust isn't a solid shell. It's broken into massive puzzle pieces called tectonic plates, and the boundaries where they meet are crisscrossed with thousands of faults. These faults constantly grind, stick, build pressure, and slip. Most of the time, these interactions produce tiny quakes we barely feel. But here's the important part. Every fault is connected to other faults, directly or indirectly. Think of the Earth like a gigantic web of tension. A small quake anywhere in that web doesn't just release energy, it redistributes it. When a fault slips, it changes the balance of stress around it. Sometimes that means reducing the stress on nearby faults, making them less likely to rupture. But other times, and this is where the chain reaction begins, a small quake can add stress to a neighboring fault, pushing it closer to failure. Even a magnitude 4 can load stress onto a segment of fault, holding back a magnitude 7 or 8. So earthquakes aren't isolated flashes of energy. They're part of a continuous, interconnected system, and that system has breaking points. The science behind a chain reaction, stress transfer. The key mechanism behind earthquake triggering is something called Coulomb stress transfer. In simple terms, when one fault slips, it reshapes the stress field around it. Imagine snapping a tight rubber band. The band doesn't just break at one point, the tension shifts through the entire band. In geology, a small quake may slightly loosen one area, but it may push another area over its limit. If that second fault fails, it may destabilize a third. If the third fails, it may destabilize a fourth. This is how a chain reaction begins. Scientists use advanced models to calculate which areas gain stress after a quake. More often than you'd expect, the next major rupture happens exactly where the stress was transferred. This doesn't mean every small quake triggers a bigger one, but it does mean small quakes can act as catalysts, nudging an already unstable fault toward catastrophe. The cascading failure effect. When a system starts to collapse, think of the Earth's crust like a giant, fractured Jenga tower. Everything is balanced until one block moves. In a chain reaction earthquake sequence, a small quake strikes. It might be harmless on its own, but it changes the stress map. That stress travels, not randomly, but along predictable fault lines. Another fault weakens. Maybe it was already close to failure. Maybe it's been accumulating pressure for centuries. The second fault ruptures. This rupture triggers additional stress redistribution. A larger, deeper, more dangerous fault finally snaps. And this becomes the catastrophic, headline-making monster quake. In some cases, the entire process happens in minutes. In others, the triggering event takes hours, days, or months. This domino effect is why some major quakes have frightening foreshock sequences, a cluster of small quakes that precede the main event. The foreshocks don't always look important until after the fact. Sometimes the quake that starts it all is so small that only seismometers detect it. Real examples when small quakes triggered monsters. The 2011 Japan megaquake, magnitude 9.0. Before the catastrophic Tohoku earthquake, scientists observed a cluster of smaller quakes, including a magnitude 7.3 foreshock just 2 days earlier. Stress modeling now shows that these smaller ruptures likely destabilized the massive section of the subduction zone that unleashed the 9.0 quake and the devastating tsunami that followed. Turkey's 2023 twin earthquakes. The first 7.8 quake transferred enormous stress along the East Anatolian Fault. Just 9 hours later, a second fault segment ruptured with a magnitude 7.5 quake. This is chain reaction behavior in real time. Landers, Hector Mine Sequence, California. A magnitude 7.3 quake in Landers, 1992, triggered a magnitude 6.5 aftershock 40 kilometers away. It also reloaded stress onto the nearby fault. 7 years later, the Hector Mine 7.1 quake struck, in almost exactly the stress-loaded region predicted. Small and large quakes are connected far more often than most people realize. Why some small quakes don't trigger big ones? This is important. Not every small earthquake sets off a chain reaction, because not every fault is close to failure. For a chain reaction to produce a monster quake, 3 conditions must align. A major fault must already be critically stressed. If the fault is not near its breaking point, a small quake won't trigger it. The triggering quake must add, not reduce, stress in the right direction. Stress has direction. If the slip doesn't push the fault toward rupture, nothing happens. The faults must be mechanically connected. Some faults interact strongly, others barely affect each other. This is why predicting earthquakes is still one of science's hardest challenges. It's not about detecting the small quakes, it's about understanding the stress state of every fault around them. Why chain reaction quakes are so dangerous. The worst thing about chain reaction earthquakes is that they strike fault systems, not single faults. This means larger areas are affected. A single megaquake can rupture one fault. A chain reaction can rupture several, spreading destruction across entire regions. They can happen faster than warnings can be issued. A foreshock may occur minutes before the main shock. Not enough time for mass evacuation. They are often misinterpreted. People feel a small quake and think the danger is over. But in a chain reaction scenario, the danger has just begun. They can produce unexpected megaquakes. Many historic monster quakes, Japan 2011, Chile 1960, Alaska 1964, came after periods of smaller stress accumulations. Chain reactions don't just create big quakes, sometimes they create the biggest quakes ever recorded. Could a small earthquake today trigger a massive one tomorrow? The honest answer, yes, but only if conditions are right. Scientists can identify fault systems capable of chain reactions. California's San Andreas system, Turkey's North and East Anatolian faults, Japan's subduction zones, Cascadia, Pacific Northwest, Pakistan and Afghanistan's connected fault networks, the Himalayan megafault. These systems have long, stressed fault lines that can transmit energy across great distances. A small quake near one of these faults doesn't guarantee a larger one, but it can be the first falling domino. This is why seismic monitoring is so critical. The small quakes aren't noise, they're signals, whispers from the earth, that may reveal where stress is shifting. Final thoughts. Understanding the chain reaction model makes us safer. The chain reaction model is both terrifying and empowering. Terrifying because we now understand that earthquakes aren't isolated events. They are part of a connected, high-stress network beneath our feet. A harmless tremor may be redistributing stress onto a fault waiting to rupture. But empowering because this knowledge gives scientists tools to predict which faults are now more dangerous, identify where stress has accumulated, improve building safety codes, strengthen early warning systems, monitor foreshocks more effectively. Understanding the chain reaction model doesn't stop earthquakes, but it does help us prepare for them.